Hello, everybody. I'm Paolo Fioravanti, CEO and co-founder of Circus Data at HELLAS. I'm going to talk about how our company is trying to revolutionize the semiconductor connectivity, and in particular, how our technology applies to a next generation of flat phase antennas. I will talk a little bit about our company, then explain more in detail what is our plan, what is our technology, and what it could entail for the ecosystem of telecommunication and SATCOM telecommunication. So our company is, the vision of our company is to facilitate access to faster, ubiquitous, and downstream communication around the globe. We envision ourselves to become a leading chip supplier provider for the SATCOM market, and to integrate our proprietary technologies to accelerate upon our vision. The team is a growing team. We're about 20. We're based in Greece, in Athens. And me, my CTO and the CCO are leading the activities with about other 18 engineers, of which more than 30% are PhD level. Why am I doing this? Just to introduce our company that has been around for a while. Although we're founded in 2018, we already delivered on a number of R&D projects in Europe, especially working on the same kind of technology we'll be describing today. Sorry if my voice goes and goes. So I've been working in EDF projects, doing exactly what I'm describing in the next of the presentation, integrating in 3D structures, a compound semiconductor with silicon for advanced SATCOM and high power, high frequency application. The core skill set of our company is all about IC design, and either on silicon or on 3.5 compounds. And we've been operating in design service mode for the past 5 years, and lately moved to our own product development for SATCOM application. What we are offering and what is core technology and what we work on is advanced package integration and system package and antenna package solution. So said this, we have decided to move in the SATCOM market, and in particular to the space sector. Why? Because as it will, for reason it will become clear in a while. Our solution creates a definite advantage for this kind of integrations, and all that in a market which is huge. SATCOM is above 1 trillion expected in 2032, and the flat panel antenna are expected to be in the range of 18 billion market. So the market is already populated, but our technology is agnostic to the application. So we intend to send the chip, not the full solution of the antenna. And we believe there can be a great penetration. So just for you that don't know, I don't believe anybody is unaware. But what we're working on is basically delivering on next generation flat panel antennas. So these are low-technical antennas where the building element is a matrix of patch, flat antenna elements, which, if controlled in rows or in columns all together, allow eventually, by applying a delay to the transmission, to direct the beam in any desired direction in the space. So that's why it's called beamforming. You control delay or phase, and you are able to steer the transmission direction as you wish without any mechanically moving part. It's a very, very cool concept. And how are these applied? So everybody knows about Starlink. Everybody knows how much a player it has become in the last few years, reaching about 70% of the entire market of flat panel antennas. Each of these antennas has about 1,000 chips, 600 to 1,000 silicon chips integrated on a PCB. So it's a huge number of components for an area which is about 1 meter square, and needs to be properly engineered to work seamlessly. the issue with space is even more dramatic. So it's already a big antenna, but there are 4, 6, or 8 panels integrated in each satellite. This means a solution which is large, it has a high complexity, a large weight, and it costs a lot to bring to orbit. So there is definitely the need for optimization in order to reduce the cost to orbit to release this huge antenna. And we believe as Circus integrated to have a solution. But how would you reduce the size of such antennas? So if you think of the transmit side, this means reducing the number of elements. Intuitively, if you follow the graph, you go from a large number of elements with low power to a low number of elements with the higher power. But what we see in the market is antennas which are large. And these are antennas which are flat, yes, but built on silicon. So to reduce the area of these antennas, you would need to actually increase the number of the power per element. And, but you cannot see in the market any such antenna integrating 3.5. And basically you see antennas which are bulky, classically tiled, called steerable antennas. And they're even larger, more weight for the same aperture of the antenna, so for the same area that the antenna allocated to the antenna elements. So why there is no integration? Why it has not been possible? The answer is in the size of the components that are available in the market. So if you put numbers down and you start considering chipset which are actually available as components of the shelf, you can think about the matrix of antennas like a small element of a 2x2 patch antennas. This will have a physical side which is driven by the wavelength of the signal, but the frequency of the application. And so on one side you have the elements, on the other side you need to place your chips. But if you just start integrating the 3.5 components, your space is already fully used. So there is no way, at least at high frequency in the K band, to integrate 3.5 and silicon in the available space. Same if you go to lower frequency in the KU band. So in here I'm showing that the only option for high frequency is that you need to go to a tiled 3D all dimension antenna solution. If you go to KU, which means lower frequency, larger wavelength, more space, still you will be able to place more chips, enabling more complex antennas, but you will still not be able to integrate all the chips needed for a shared aperture, so for an antenna which transmits both TX and RX function, which means that you will have at the end 2 beamformer, one for the TX, one for the RX, side by side. So where I'm going with this? I'm going to the direction, sorry for the slide positioning, of Circus integrated innovation. What we can do to resolve this situation and be able to integrate in the same aperture TX and RX, 3.5 and silicon. This is an obvious answer. You need to go vertically, so you need to stack chips. This is the trend in silicon integration with chiplets. Intel has been pushing it for ages. TSMC is implementing it as well. But this is not happening at high power, high frequency because of thermal issues, electromagnetic limitation, losses, a lot of complications, which we believe as a company we can address by pushing forward in our technology. And that's the reason for me being here to present to an extent what we have done, what we can do in this market to achieve the goal of shared aperture, small size antennas. And this is basically Kythrion. That's how we named our technology platform, which comes from Greek, being a Greek company. It's a Kyma, which means wave, and Thera, which means portal. So wave portal, a bit cheeky. but nice name. And in here we show what are the innovation and where they're placed in this structure in a 2x2 element kind of approach. We have integration, we have innovation at the antenna interface with the 3.5, at the architecture of the chip in terms of TX and RX co-design with the antenna, at the actual design topology and methodology for the 3.5 chips, and all the placement in the package, the material, and the thermal solution that we have used to enable high power at high frequency. And this, at the same time, packed with all the features you would expect from a silicon beamformer, so high performance, high controllability, and what you would expect for a very good 3.5 front end. Decently high power in the watt range or above at Ka, and a very low noise figure, achieved by integrating and co-designing the interface with the antenna element. And then all the features that I mentioned before implicitly. Heterojunction, fitting the grid of the phase array, half the wavelength that is, and enabling state-of-the-art multi-beam functionality in an analog beamforming kind of implementation. And then now comes the cool part. So this is just to describe what the technology could enable. In this slide, you see an assessment of with calculation showing that by meeting the same performance of what existing antenna do, the Starlink one, with the Kythrion chip, you would use less than half of the area. So this is just to show that how the miniaturization by stacking the component vertically could reduce the size as well as the weight and the cost of the antenna. But that's not just it. If you think of an application in the space side, then all multiplies greatly in terms of return on investment and enablement the technology can bring. If you think of the vector, from Starlink, the cheapest one nowadays, the Falcon 9, by a simple calculation, you can understand that for every launch, if you had to replace the antenna with the technology based on Kythrion, you would get a saving of about $20 million per launch. And with the reduction of weight, a number of other advantages. So extended the lifetime of the satellite, because less weight means less atmospheric drag. And or enable the satellite provider or the service provider, for example, of Earth observation, to deploy more services on the same satellite for the same launch cost. And this on top of what the technology could enable on the standard SATCOM market. So just to give you another example of how this could improve Earth observation, for example, again. Currently, these satellites are transmitting down information using X-band fixed antennas because they fit, because they are simple enough to enable a decent communication channel, and they're transmitting for every flyover to the ground station about 150 gigabytes of data. If those antennas had to be replaced with one new unit, RX and TX beamformer using Kythrion, they would be able to transmit about 15 terabytes of data every flyover, which means more or less a 20x improvement of bandwidth and information, which would enable real-time raw transmission of data from Earth observation satellites. Things that are now not happening, and that are pushing these companies to consider using AI to optimize their data. So I'm pretty close to the end. To summarize, we offer a next generation solutions for the flat panel antenna market to serve the SATCOM, but also ground communication because of the flexibility of the platform. A technology which would be easy to to deploy, which will enable ubiquitous connectivity, being the most suitable for space implementation, and to follow on our mission of downtown free communication.